Hello, my name is Russell Fox, and today I'll be doing a preliminary design review of the dryer efficiency module. And my teammate is Jason Belk, and our mentor is Dr. Scher. The outline of this presentation consists of a project description, the cost of the project, the timeline of the project, and then we'll talk about the different parts of the project. One part is a dryer test set. The next part is a conceptual circuit for a dryer efficiency module. And then the last part consists of the final design of the dryer efficiency module. Then at the end we'll wrap up with a summary. So, project description, the motivation is to design a dryer efficiency module. This module will turn off your dryer when your clothes are dry. Dryers are notoriously inefficient home appliances. They continue to dry clothes even after they're dry. So the project consists of the first two parts is the dryer test set. The dryer test set will measure and acquire data that we will use to help design the second part of the project, which is the dryer efficiency module. And this module, like I said, will turn off your dryer when your clothes are dry. So we have to design a test set that will drive the design of the dryer efficiency module by the data we collect. Requirements are to design hardware and software for a dryer test set that will acquire data during an entire cycle. Another requirement is to obtain a dryer to perform these tests on and a control sample of clothes to perform these tests on. We have to analyze the test data, and this test data will again drive the design of the dryer efficiency module. And we'll also design improvements on our conceptual circuit. We'll test our design, and then we'll document the entire process throughout. We have a timeline, and we're approximately almost 200 days in, and we are in prototype testing. So we are ahead of schedule, and the project is going according to plan. Here you have the cost of the various hardware. Total right now is $347.22. The dryer test set general description. The test set acquires data from 4 sensors. The 4 sensors is a current transformer, which reports current. There's a relative humidity / temperature probe, and then there's an airflow probe also. The airflow probe and the relative humidity and temperature sensors are in the exhaust of the dryer. The current transformer is measuring one leg of the 240 volt split phase AC that's going into the dryer. That leg consists of the motor and also the heating element. So one leg is just for the heating element, and the other leg is for the heating element and the motor also. That's how dryers are designed. So the dryer test set, we have some testing goals for performing testing on the control sample of clothes, and the goals are to understand what the relationship is between those 4 sensors, and also what is the key indicator when the clothes are dry of those 4 sensors. So as you can see, we've ran some tests, and this is an example of a cycle that we recorded here. The red represents relative humidity, which starts out around 20%, goes to 100%, then comes back down to 0. Here, blue is temperature, which starts at about 19 C and then goes up to about 58 C and then falls below 30 C. Here you see the current. The current is 23 amps when the heating element and the motor are both on at the same time. When you see the current fall to about 2 or 3 amps, that's when the heating element is off and the motor is turning that drum of clothes. The drum which spins the clothes. So obviously there's more current being used when the heater is on. So our testing results pretty much told us nothing. They didn't let us know when the clothes were dry from the 4 parameters, the 4 sensors that we're collecting data on. So what we decided to do was research humidity and decided that maybe we should be looking at absolute humidity. And we found a formula, and this formula will give you absolute humidity in grams per meters cubed, and you can calculate it with relative humidity and temperature. We found this formula from a gentleman, Peter Mander, who is a physical chemist by trade and has a blog. So we used his formula in calculating absolute humidity. Formula is very accurate. Tested it to a lookup table. It's within 0.3% of up to 40% relative humidity. So it's a very accurate formula. So now you see the same testing results, but only we've included absolute humidity. And what you see here is the absolute humidity starts out at about 5 grams per meter cubed, and then it comes back down to about 5, comes up again, goes back down to 5, comes up to about 3, and then kind of tails off here to 0. So when we were looking at the data, what this told us was it starts at X point, the absolute humidity. And what we're looking for is for it to reach X point. And that tells us that the clothes are getting dry, they're getting there. And that's a good indicator. So what we did is we designed a conceptual circuit that when the absolute humidity is being monitored, that we would turn off the heating element by a relay and let the clothes go through a cool down process for 6 minutes and then cut the dryer completely off. So the conceptual circuit consisted of using our test set to drive the relays. It wasn't a standalone system. So we had a personal computer, the data acquisitions card, we had the probes in there, and a the power for the probes, shunt resistors, and we also had this relay module, this Altronics relay module, and we used a digital output from the data acquisitions card to turn on and off the relays. Here you have a hardware schematic of our conceptual circuit. You have the relative humidity and temperature sensor. That's right here. Here you have the airflow sensor, current transformer sensor, and you notice the current transformer sensor and the relative humidity and temperature sensor both have shunt resistors. So it's based on current, and the current is dropped across the shunt. That voltage is read into the data acquisitions card, which is represented by this block right here. So channel 1 is for relative humidity, or excuse me, channel 0 is for relative humidity, channel 1 is for temperature, channel 2 is for airflow sensor, channel 3 is for current transformer, and all these channels are differential. And here you have the digital outputs that I was talking about earlier from the data acquisitions card. The D0 goes to the heat relay, which turns on and off the heating element by opening one side of the 240 volt split phase. And then there's another relay, which is a D01, the output of the data acquisitions card, and this will turn off the motor. And when you turn off the motor, you kill the dryer. Everything turns off. Here's a little bit further down schematic into what the relays are actually driving. You see here you have the data acquisitions card. You have D0 and D1 going to relay 1 and relay 2. Here we're calling them relay 1 and relay 2, but it's one's for the heat and one's for the motor, and you can see that represented right here. And the rest of this is just the internals of the dryer. You can see a fuse, a door switch. Here's the motor. Here's the heater, and these thermostats here, they're operated on temperature, so once they get to a certain temperature they open and close. That's just inherent to the design of the dryer, but really not important to what we're doing. So the software for the conceptual design of the circuit was written in LabVIEW. Here's the front panel. We have here all the sensors and the controls, start and stop, log time. We're still acquiring data. Here we have a LED, which is an indicator of when the clothes are dry and wet. It's blue when they're wet, and then it turns red when they're dry. We're still graphing all of the sensor data from the test set, and indicators are the same as it was in the test set, which were just having a numeric indicator of what those sensors are. And then we have a start time, start date, and elapsed time. It's a timer of when it takes the next data sample. Here we have a block diagram of the software. It's like a flow chart. So we start, goes to the user interface. If the stop button is pressed at any time, the program stops. The next step is once the user puts in the parameters for testing and presses start, it displays the start time. The initial value of the absolute humidity is stored, so it knows where to start. And then it asks if the file exists, because it saves the data to a file. If it does not exist, it creates a file, and then it writes headers for that file. Comes back to here. Then it records, displays, and graphs the data. The data acquisition timer counts down until what the user put in. So if you put 5 seconds, it'll count down to 5 seconds, then pull the data. Then it acquires data from the sensors, and the absolute humidity is compared to the original that was stored right here. And if it is equal to each other, then the next step is it opens the normally closed relay for the heater. So it turns off the heat, and then goes into a cool down cycle for 6 minutes before it turns off the other relay for the drum motor. And remember, it turns off the dryer once you kill the drum motor relay, then it ends the program. So that's how it works. So we did some testing of the conceptual circuit compared to an automatic setting. So you see here in mode, efficiency is the conceptual circuit. We're calling that efficiency mode. And then automatic is the automatic setting on your dryer. So as you can see, the yellow is compared to each other. The blue is the same, green, and then this orange color here. And so, in the two different loads, so there's cotton, blended, and at the end of the day, what we found is that in this efficiency setting, for low heat, cotton load, the total kilowatt hours was 3.21 as opposed to 4.41 for the automatic. And the cost was about 32 cents, here is 44 cents. And then the time was 76 minutes, and here is 40 minutes. And the total difference in kilowatt hours is 1.2, and the cost difference is 12 cents, and the time savings is 36 minutes, which I was impressed with. You know, you save time, you save money. The cost was calculated at 10 cents per kilowatt hour. That's what it is here in Wake County. That's what I pay for my power. So that's how it was calculated. So just to kind of go down the list here, you see we saved 89 cents in low heat in the blended. We saved $1.43 in the cotton for the high heat, and $1.60 for the high heat in the blended. So that's major savings in time and money. It's represented right here. Adds up over time. So here we have a final design. The final design will be driven by a microcontroller. You won't have a computer or no lab view. It'll all be written in C. So what you have here is a controller. The controller, we decided to have the capabilities to talk to a computer if somebody wanted to plug a USB cable up to it and through an executable have some functions where they could maybe see how much money they're saving, see how the dryer's performing, maybe do a comparative what it does before you install the module or you put it in efficiency mode, maybe compare different modes like automatic, timed, and then efficiency. Efficiency would be the mode that is driven by the dryer efficiency module, but the automatic and timed would be inherent to the dryer design. And then just kind of compare those and see what the cost savings is, and you know, the footprint on the environment, and just the benefits there, and also time savings, and also wear and tear on your dryer. It saves wear and tear on your dryer, and your clothes, they won't shrink because you won't over dry them. So all those benefits can be quantified through an executable written in LabVIEW for your computer, so you can monitor all that. But anyway, there's a power supply that's supplying your controller. Your controller is talking to a current transformer, is also acquiring data from a current transformer. The relative humidity and temperature sensors are still into play. They're in the exhaust. Relay driver, then you have two different relays for the drum motor and heating element. The current transformer will be good because in case there'll be two current transformers and one on each leg, and it'll tell the microcontroller which one is for heat and which one is for the motor. So this is a software block diagram for the final design. You start the dryer efficiency module is turned on. If the off button is depressed, it ends the program, so kind of like an emergency stop. The initial value, the absolute humidity, is stored again. The data acquisition counts down 2 seconds. It acquires data from the sensors. It compares the absolute humidity to the original stored absolute humidity. If the absolute humidity is less, -1, it opens the normally closed relay for the heat. It waits 6 minutes, and then it opens the normally closed relay for the motor, and then turns on a dry LED indicator. So there's a couple things different here that you may have noticed. Is it's smaller because it's a standalone system. Again, it's not running on LabVIEW. It's a microcontroller that's just running the functions of the efficiency module. So to sum up, what we talked about is the final design was designed through interdisciplinary practices between teammates. My partner, he's experienced in home appliances and repairs and troubleshooting. My experience is in data acquisition, testing systems, circuit design. So it was a good pairing there, a good match. The final design was data driven. We went about it the right way. We had tests performed to let us know, what we needed to have our final design designed around. And again, that stems back to the absolute humidity algorithm. That was the home run in this case. We've proven that the conceptual design works because it's a time saver, it's a money saver. It saves wear and tear on your dryer. It prevents clothes from getting shrunk. We're going green. It's just, there's so many benefits there. It's a very robust design. The project is on time and budget, and the reason that it is because of planning, lean development practices, and also lean procurement practices. So in closing, I would just like to say that I'd like to thank Jason Belk and Dr. Scherer for their help and input into this project. And have a nice day.